All right, now that we have looked at polynomials and pretty much everything there is to look at polynomials, we're going to get into combining polynomials in a certain type of way to create what we call rational functions. Now, to do this, a rational function, the root word there is ratio, and of course a ratio is a fraction. So what we're going to do is we're going to create fractions where the numerator and denominator are polynomials. Okay, so by definition, a rational function, I'll call it r of x, is equal to a polynomial, p of x, divided by another polynomial, I'll call it q of x. Okay, so p of x over q of x, that's a polynomial over another polynomial. Okay, where p of x and q of x are polynomials. And there's one very important aspect, is that you cannot have a fraction if the denominator is 0. So we have to make certain that the denominator is not 0. Okay, so that means q of x cannot equal 0, right? And that's going to lead us to finding the domain of these things, okay, these rational functions where you have a polynomial on top, polynomial on the bottom. Any number that makes the denominator 0 is not going to be in the domain of this rational function, because if the denominator is 0, the fraction will be undefined. Okay? So any values of x such that q of x equals 0 will be excluded from the domain. Okay, so that point will not exist on the graph. There won't be a point on the graph at those numbers or at those x values. Okay, so we've seen one example of a rational function in the past. It's called the reciprocal function. We'll talk about that in a moment. Just, you know, as a general, in general, your rational functions, you know, give you an example, something like 2x squared minus 5x over, you know, x plus 7. That's an example of a rational function. Polynomial on top, polynomial on the bottom. Okay. Now, it could be any degree. It doesn't matter what the degrees are. I just threw a random one up here. Okay. Now, let's take a look at that reciprocal function. It's the one that we've seen in the past when we dealt with our library of functions. It's the 1 over x function. Now, this is technically a rational function. We have the polynomial 1 over the polynomial x. It is monomials on top and bottom, but it's still polynomial, so we'll consider it a rational function. Now, in this rational function, remember, the graph of this thing had both vertical and horizontal asymptotes. Okay, we kind of went through how that develops, because you cannot plug in 0 into this function, right? 1 over 0 is undefined. And so an x value of 0, which is right on the y-axis, does not exist on this graph. But remember, what we saw was that the graph of the reciprocal function has a vertical asymptote at the y-axis, a horizontal asymptote on the x-axis, and on the positive x values, you get positive y values, because 1 over a positive number is still a positive number. On the other hand, with negative x values, we had negative y values, because if you take 1 over a negative number, it's still a negative number. Positive over a negative is still negative. So you had this mirror image reflected through the origin, where you still had your horizontal and vertical asymptotes on the axes. Okay. Okay, and then we determined that from that, the domain was going to be all real numbers except for 0, right? The x value of 0 does not appear on in the domain, and so that would be negative infinity to 0, union with 0 to infinity, if I were writing it in interval form, or I could write it in set form and just say it's all values of x such that x is not equal to 0. Okay, and we assume x to be a real number when we write these. All right. Okay, so either one of those notations, but they represent the same thing. Okay. Now, of course, the range is identical because on this graph, the y value of 0 is also not hit by the graph. But I'm really going to focus on the domains here in the rest of this discussion. Now, if I were to do some transformations with this graph, we've seen all of our vertical and horizontal transformations. If I were to take this graph and I were to shift it vertically, right, that's just adding or subtracting a number to the whole function. I'll give you an example. If I had a new function, I'll call it g of x, and I want to go 1 over x plus 3. Okay, take the reciprocal function, add 3 to it. Well, shifting this vertically is not going to move the vertical asymptote. Vertical asymptote stays the same, and of course 0 still makes the function undefined, so that goes together. But the function then, the graph simply moves up 3 units. So instead of there being a horizontal asymptote at 0, it's now going to be over at 3 or up at 3. Okay, so 3 units high, that's your horizontal asymptote. But then the graph, basically the shape of the graph is going to be the same. So you're going to have this one portion of the curve up to the right and another portion of the curve down and to the left. Still bounded by the same vertical asymptote, but now a new horizontal asymptote shifted up. Okay, and of course we can do that same sort of thing, but as long as you're not changing that denominator, the vertical asymptote won't change. The vertical asymptote is going to stay right at 0. However, if I were to change the denominator, take a look at what that would look like. For instance, if I were to shift this graph horizontally, let's say to the right 2 units. So I'd have maybe h of x equals 1 over x minus 2. Remember, if you replace the x with x minus 2, that's a right shift of 2 units, okay? And so what I would get is now the same sort of graph, same shape, but now the vertical asymptote is not at 0, it's going to move over to 2. Okay. So our vertical asymptote changes, and again the general shape of the graph will remain the same. We're going to have part of the graph up on the top right and part of the graph on the bottom, on the bottom left. Okay, something like that. Okay, and so x equals 2 is going to be your vertical asymptote here. Now notice 2 is the 0 of the denominator. Okay, it's the number you would plug in to make the denominator 0. And in fact, that will always be the case. Your vertical asymptotes should correspond to zeros of the denominator. Okay, so that's going to be a general rule that I'm going to go ahead and set aside for a moment, so that vertical asymptotes occur at zeros of the denominator. Okay, so vertical asymptotes occur at zeros of the denominator, and that's always going to be the case. However, there are some zeros of the denominator that don't correspond to vertical asymptotes. I'll show you that in just a moment. Before I do that, think about fractions for a minute, and think about what would happen. Think about how you would get an answer of 0 from a fraction. right? So if you had two numbers, say a over b, what would you have to plug in where to get a 0 as an output? Well, you'd have to have a 0 on top, right? If you had 0 over anything, that's going to equal 0. And there's not really any other way to get 0 out. So that means that anything that makes the top, the numerator, 0, will result in a 0 or an x-intercept of our graph, okay? Because the output will be 0. The height of the function is 0, okay? So anything that makes the top 0 really makes the whole thing 0, with an exception I'll mention in a moment, okay? So in general, x-intercepts occur at zeros of the numerator. Okay, so that kind of makes sense. So if the top is 0, the whole fraction is 0. If the bottom is 0, the whole fraction is undefined. But what happens, and here's the exception, what happens if both are 0 at the same time for the same x value? Okay, well that could happen if your function was something like, let's say, x squared minus 2x over x minus 2. Okay? You might not notice this right away, but this function at a value of 2, if you plug in 2, you get 2 squared on top. 2 times 2 is 4, and then 2 minus 2, and what you'll end up with is 0 over 0. Well, that's strange because we just got done saying if you have 0 on top, the answer is 0, but if you have 0 on the bottom, the answer is undefined. So which one is it? Well, the undefined kind of rules out, okay, rules the day here. These things are also undefined. 0 over 0 is undefined. And so we still have an undefined point. However, if you'll notice, we can reduce a rational function by factoring it and canceling common factors. It's the same idea you would use to cancel numerical fractions, right? So here you could factor this out, factor out an x, and you get x minus 2, and then here factor out x minus 2, or it doesn't factor, I'm sorry, just write the x minus 2, but I'm going to write it as though it looks like a factor, so it's all grouped together. And then I can cancel the common factor of x minus 2. Anything divided by itself is 1. And if 1, then we have 1 times x, which is x, okay? So what we would have on this rational function, the graph is actually going to look like the graph of x, which is just your identity function, right? It's a line going up to the right. Except at this point of 2, there can't be a point on the graph, right? It's undefined there. And so what you have, if this rational function is exactly the same as our identity function, except at 2, then you have a line, right? This is our identity function, x. But at 2, you don't have a point. There's just no point there. It's what we call a hole, okay? A hole in a graph occurs when both the top and the bottom are 0, okay? So holes occur at zeros of both the numerator and the denominator. The rest of the graph, the rest of the graph of the simplified function will be the same as the graph of the unsimplified function except for the holes, okay? So holes occur at zeros of both the numerator and denominator, okay? So if we're trying to find different features of the graph, once we get a rational function, if you look at the zeros of the numerator, numbers that are zeros of the numerator only will give you x-intercepts. Numbers that are zeros of the denominator will give you vertical asymptotes, and numbers that are zeros of both will give you holes. okay? And so we're going to start our study of rational functions by exploring the zeros of the numerators and denominators, okay? So let's take a look at an example where we kind of work this out. And remember that the zeros of the denominator, regardless of whether they're zeros of the denominator only or of both, are going to be pulled out of the domain. So we can really find four things now. We can find all the wholes, the x-intercepts, the vertical asymptotes, and the domain of a rational function just based upon the zeros of the polynomials that make them up, okay? So as an example, if I had the function f of x equals, let's do maybe x squared minus 9 over x squared minus 3x, then all I need to do is again find the zeros of both the top and bottom and then just categorize things as needed. So if I look at the zeros of the numerator, I would take, I'll do it off to the side, I would take x squared minus 9, set it equal to 0, and this I would solve by factoring, right? X squared minus 9 factors into x plus 3, x minus 3. Right? The difference of squares will always factor into two sets of conjugates, or a set of conjugates, sorry, two conjugates. And then you set each factor equal to 0, and of course we know that the zeros are just going to be -3 and +3, okay, off of that. Now I can't make a determination on whether these are x-intercepts or wholes yet until I know what the zeros of the denominator are. So let's go ahead and do that. This denominator, and I'll just work this one out directly underneath so as to save a little space. The denominator here, I could factor out a common factor of x, and that gives me x minus 3 left over. And if I set that equal to 0, then I set each factor equal to 0, x equals 0, x minus 3 is 0, and here x would equal 3 when I add 3 to both sides. And so now what I have are 2 zeros in the denominator, 2 zeros in the numerator, but notice one of those zeros is shared. The number 3 is a 0 of both. And so in this particular case, we would say that the whole occurs when x is equal to 3. So let's summarize this, get all the information we can off of those two polynomials. And the first thing I would say then is that there's a whole at x equals 3. Now, of course, to get a whole, you need the ordered pair. You need both coordinates. And so to get the y value, remember, if you plug a 3 into this function, you're just going to get 0 over 0. There's no value there. It's undefined. But if I first reduce this polynomial, which I could do by dividing out the common factor. Let me rewrite this somewhere. Let's see, let's do it over here. So x squared minus 9 over x squared minus 3x. Well, if I factor it, you get x plus 3 times x minus 3 over x times x minus 3. Okay. And so the x minus 3's will cancel out because there's a common factor there. And that leaves you with just x plus 3 over x. So if I take that function, that's our reduced function, and plug the 3 into it, I will be able to find the y value of that whole. Okay, but only in the reduced form, because the unreduced form, remember, is undefined at 3. So if I plug in my 3, imagine 3 plus 3 is 6, over 3 is 2. Okay, so in fact the whole is at the point 3 comma 2. That's the point that just won't exist. That's what we're plucking out of this graph. Okay, now once I've established that, I can say that the numerator here gives me x-intercepts, the zeros from the numerator. So there's an x-intercept at -3, 0. And I know that the numbers that are zeros of the denominator only, which is 0, will be a vertical asymptote. So I'm going to get a vertical asymptote at x equals 0. So that would be the y-axis again. Okay. All right, so that gives me quite a bit of information. I also can find the domain from this. The domain is everything except where the bottom is 0. So I've got to pull out both 0 and 3. All right, so the domain then, remember, I can pull out the 0 and the 3, both come out. And so the domain of this function is going to be, if I wanted to write this in set form, it would be all values of x such that x is not equal to 0 or 3. Those are the two values that made the denominator 0. Okay. In interval form, I could write that out. It's everything less than 0, everything between 0 and 3, and everything to the right of 3. So that would be what? Negative infinity to 0, union with 0 to 3, union with 3 to infinity. All right, so those are my 3 intervals that contain every number on the number line except for 0 and 3. So that'd be my domain. So either notation is fine for me, but when you're turning in or submitting your homework on my math lab, just make sure to read the instructions on which form it prefers. Okay. Okay, so that gives you a pretty good idea of these 4 main pieces of information that you can find very quickly about a rational function, just simply based upon the zeros of the numerator and denominator of that function.